So now we get to answer the question that has been plaguing us all year. At least it's been plaguing me all year. I'm not sure about you guys. But from the time I first learned or started to learn chemistry, there was this question in my mind. Why is it that some things, when we mix them together, react, and other things, when we mix them together, nothing happens? And there's kind of two reasons for this. One is that maybe they are reacting, but they just react so slowly that we don't notice it, and that does happen in some cases. And that's called a kinetic limit or a kinetic control of the reaction, where it's just so slow that nothing happens. But there's also this idea that no matter how long you wait, this reaction is never, ever, ever going to occur. And this is a thermodynamic barrier to the reaction, and that's what we're going to talk about today. So previously in this course, we've talked about enthalpy changes and how some reactions, they release energy in the form of heat, and some reactions absorb heat. And, as you think about these reactions, it would make sense that, the reactions that release heat, the reason why they're releasing heat is because the energy of our products is lower than the energy of our reactants. And so there's this lowering of potential energy, which would favor a reaction being spontaneous, just as a ball rolling down a hill is a spontaneous process. It would make sense that a chemical system, a chemical potential energy lowering over time as it goes from reactants to products, would also favor it being spontaneous. And that's absolutely true. However, we talked about entropy as well, and this idea that there's the second law of thermodynamics, which says that for any spontaneous process, that the entropy of the universe needs to increase. And so you can imagine a situation where maybe the chemical potential energy decreases, but in the process of decreasing, that there's like a decrease in disorder or increase in order. In other words, maybe water freezes below the freezing point and turns into ice. That's a spontaneous process, but there's going to be this increase of order. It's going from a liquid to a solid, and so the question is, why would something like that happen? How can we predict whether that would be spontaneous or not? Because again, water freezes into ice. It's an exothermic process that releases heat. It lowers potential energy, and the energy of the system as ice is the potential energy of the system as ice is lower than the potential energy as water, and yet we have an increase in order. Okay, we have a decrease in entropy. And so there's this need to pull these two things together. This idea of decreasing of chemical potential energy, as well as this idea of the changing entropy of our system. And so these two things are pulled together in this thing that we call Gibbs free energy. And thankfully, the letter that we use to abbreviate actually reflects the name. We use big G to represent Gibbs free energy. And what this represents is the amount of energy available in our system usually we say for work to be done, or we say it's the amount of available energy. So what the Gibbs free energy does, and you can see it in this, oops, let me do that. You can see it in this equation right here, is that it ties together this idea of the change of enthalpy, this release of heat or absorption of heat, with the change of entropy of our system, this delta S of our system. And it turns out that this equation, both these things combine to determine whether a reaction is spontaneous or not. So this, at the end, is the ultimate kind of arbiter or decider, or the way we decide that whether a chemical reaction will be spontaneous or not. We calculate the Gibbs free energy change that would occur during the reaction, which is the combination of the enthalpy change that occurs and the entropy change that occurs. And when all is said and done, if delta G is negative, then the process will be spontaneous. And if it's positive, if there's an increase in free energy, then the reaction is non-spontaneous. So, you can think about various situations where, maybe delta H is negative and the reaction is exothermic. We have an increased entropy during the reaction that occurs. In this case, delta G will always be negative, and so it will be, this reaction will be spontaneous at all temperatures. Okay, there's not a temperature you can find where this reaction will not eventually occur if given enough time. We'll talk about this in the next slide and this too. So there are, there are kind of questions. If the signs of both of them are the same, in other words, if you have an exothermic reaction but you have a decrease in entropy, or you have an endothermic reaction but you have an increased entropy, then there will be some temperatures at which the reaction will be spontaneous and other temperatures in which it won't be spontaneous. If you have a situation where it's both endothermic and the entropy decreases, then again, at all temperatures, it will be a non-spontaneous process. It doesn't mean that you can't make it occur. It just means that you'll have to do some input of energy, or you'll have to do some work on the system in order to get it to occur. And then if the change of free energy is zero, then what this means is that it's not spontaneous in either direction, and we've reached this point of equilibrium. You knew I was going to come back to equilibrium in this chapter. All right, so this kind of shows you in a visual way what we're talking about here. So if we were to have all products, so this is our reaction between nitrogen and hydrogen to make ammonia. So if we have just all products, then it'll be spontaneous going, if we have all reactants, then it'll be spontaneous going towards products. And if we were to have all products, it'd be spontaneous going towards all reactants. And eventually we'll get to this point. So we're plotting the change in free energy. So here we have a decrease in free energy, so the change in free energy is negative. Here, the change in free energy would be negative. And then eventually, at this point right down here, when we're at equilibrium, our change in free energy would be zero. Okay, and so that's reflected in here. So as I said, you're looking at this equation, you can kind of see that there are some situations where the reaction will always be spontaneous, some situations where it will never be spontaneous, and then there'll be some reactions where it'll depend on temperature. And so this table is a good one to get down in your notes because it's kind of the primer on how to keep this all straight. So as I was saying, if you have an exothermic reaction and you have an increased entropy, then at both low and high temperatures, it'll be spontaneous. The reaction will be spontaneous, and they show you an example right here. If you have an endothermic reaction, but you have a decreased entropy, then the reaction at all temperatures will be non-spontaneous. And so this, this conversion of 3 molecules of oxygen to 2 molecules of ozone will have a decreased entropy. It's also an endothermic process, and so there's no temperature at which this process will be spontaneous. In order to get this to occur, you'd have to put energy into the system. If, however, it's an exothermic reaction with with a decreased entropy, and this is the example I was using before, water turning into ice. At low temperatures, it'll be spontaneous. The reason why it'll be spontaneous is because although this is positive, okay, if T is low, and T has to be in Kelvin here, so if T is low, then this negative term, this negative enthalpy term, will kind of overwhelm everything, and it will determine the ultimate sign of delta G here. If, however, you kind of go in this reverse direction, so going from liquid to gas is an increased entropy. It's more disordered, yet it's an endothermic process. At low temperatures, it'll be non-spontaneous. At high temperatures, it'll be spontaneous, because at high temperatures, this delta S is positive, which makes this whole thing a negative. So at high temperatures, this term determines the sign of delta G. And so at high temperatures, if delta S is positive, and this is also positive, then at high temperatures, you'll have a spontaneous process. But if T gets too low, then delta G will, this will have the larger effect, and delta G will be positive, and it's going to be a non-spontaneous process.